Okay, so I just want to go over some of the law of large numbers as well as the central limit theorem because it's pretty commonly used. So the intuition with the law of large numbers here is basically that expectations or that the sample means could be really good for could be basically quite good for approximating expectations. And the central limit theorem is basically is that sums as well as sample means as will converge to a normal distribution, right? Regardless of the actual original distribution of how the xi's are distributed. So let's start with the law of large numbers. So the law of large numbers, at the end of the day, there's the weak and the strong, but the idea is just that you get a point mass, xn bar becomes a point mass to the true mean as n goes to infinity, right? So the idea is, like, let's just consider it as we have, let's say, n is 10 here, right? So let's say, so for the law of large numbers, let's say we have some x1 to x10, and we get these 10 samples from some population, and let's assume that all these are drawn ID, and we'll see why this is important. So we need this ID assumption here. We need this ID where the expectation of these xi's is some mu, and we'll say the variance of these xi is some sigma squared. And what the law, let's consider basically let's consider some facts. So let's consider the expectation of x10 bar, I guess. So this will be basically the expectation, some I, let's say from 1 to 10 of xi over 10. This will be the expectation of xi, which is mu. And let's consider the variance of x10 bar, which will be the variance of, starting from I equals 1 to 10, of, xi over 10. This will be basically the variance of xi over 10, which will be sigma squared over 10, right? So that's the idea. So basically, if we were to think of the distribution of x10 bar, it would be centered at the mu. And we would have some variance. We don't necessarily know it's normal. It could be any distribution, right? We're not saying it's normal, but let's, for simplicity, say it looks something like this. And basically, it would have some variance here of sigma squared over 10, where sigma is like the original variance of each of our random variables. So I should make a normal assumption. We're not saying anything about that. The idea is that we have some sigma squared over n. And clearly, we could say, well, imagine we have some x1 to xn, where each of them are distributed according to this, have these properties, then basically we would note that the expectation stays the same, so we're sending there, but basically the variance scales down from sigma squared to sigma squared over n. And so we can note basically that as n goes to infinity, the variance of xn bar also goes to 0. And so what's the intuition here? The intuition here is that basically the distribution of xn bar, so if this is xn bar, it's going to be always centered at mu for all n. So for all n, the expectation of xn bar is mu. However, we would say only as n goes to infinity do we get that the variance, though, of xn bar goes to 0. So that basically is basically like if n is 1, xn bar, it's like it can be very wide. And then basically as we get to like x 1,000, let's say, xn bar 1,000, or x 1,000, the sample average of 1,000, it will still be mu. However, the variance is going to be much a tighter distribution. And all the way to infinity, like I'd say x infinity, we're going to get a point mass around mu. So that basically, the intuition here is that when you take such a large sample and you take the sample average, it's just always going to be the truth. So the idea here is like, yeah, so that's the idea, is that basically the variance just shrinks to 0, which then basically means that you're always going to, more or less, the sample mean will converge to the true mean. Yeah, so that's basically in words. So I'll say in words, the sample mean converges to the true mean, which you can think of u as n goes to infinity. And this is really useful. So for a couple things, like one is like, I was thinking about this, is usually we think of the covariance between two random variables x, y, for example, as the expectation of like x minus the expectation of x times y minus the expectation y, right? So like if we were to think about it as like some integral, it would be an integral over all xy of like x minus the expectation of x, y minus expectation of y, times the joint distribution xy of xy dy dx. However, the issue is like we may not actually know this joint distribution, and we don't know expectation of x, expectation of y, and because we don't know like this joint, we can't then take the expectation. So instead, well, we're sort of like, okay, well, the idea here is, well, let's sort of appeal to the law of large numbers here, right? Let's take some 1 over n, we'll take the sample mean, and we'll then take x minus, well, we don't know the expectation of x, right? Either we don't know we don't know that. So instead we just, again, replace that with, let's say, some j equals 1 to n of xj over n times, again, y from j equals 1 to n of xj over n. So the idea here is, again, like we're just going to basically say, well, like if n went to infinity, then this would sort of, this part here would be replaced with an expectation. This part here would also be replaced with an expectation, right? And this would also be replaced. So that's the idea with the law of large numbers, is basically, it's a justification also to why you could use your empirical distribution of like your data. You only get access to, basically you would have only access to these pairs, these n pairs, and you want to compute the covariance. You have no idea about like some expectation over, like you only have access to your data, and it sort of makes sense if n is sufficiently large that this is a good case. There is I'll maybe discuss briefly about the strong and the weak form. So the strong, so the reason we need IID first, I'll say, is because here to get here, we need independence. So we need independence, and we're obviously assuming that in both here and here that they're identically distributed. So we need the ID part. Okay. So basically the weak versus strong. I'm not going to write out the mathematical, but the strong implies the weak. So if you say strong convergence, it implies the weak. That's important, as well as the fact that basically there are different types of convergence. That's the idea. So there's convergence of in probability. So you have convergence in probability, and you have sure convergence, or almost surely. Sorry, it's called almost surely. And so this is for weak, and this isn't strong. So I think in like the idea here is in strong, we say is for a single iteration, if n goes to infinity, we're guaranteed to converge on every single iteration. Here, it's sort of in probability, so we're not guaranteed to any single instance. Okay? Now I'm going to talk about the central limit theorem. Yeah. So the central limit theorem, so the law of large numbers here is regarding the sample mean, right? It's regarding xn bar. That's what the central, this is what the large law number. The central limit theorem also discusses xn bar, but we also could consider the sum from Sn bar, right, which is, or Sn, which will just take the sum of n random variables, xi, okay? So that's what the central limit theorem is about. And so like the law of large numbers, I think, is like a convergence theorem, right? It just says that the sample mean converges to the true mean. The central limit theorem, on the other hand, is about convergence in distribution. So this is convergence. Oh my gosh, my handwriting's so bad. we're talking about convergence and distribution. That's the key. So it's this convergence in distribution compared to the LLN is about convergence and like in terms of convergence and mean, convergence and expected value. Right, we're saying that the sample mean converges to the expected value. Well, here we're saying that the sample mean, we'll talk about it a bit more. So that's the high level idea. So the central limit theorem is going to be like, more or less, is we consider, let's start with some Sn. So we'll define Sn to be a sample of size n of where we have, let's say we have some some sample x1 xn from some population. Let's say it's ID with expectation of xi being some mu, and we'll say that the variance of xi is sigma squared. Okay. And so we'll define Sn to be the sum of these n random variables. Okay. So the Sn is also a random variable because obviously we sample x1 xn, we then sum that up. We could have got different x1 xn, so Sn could be different. So we'll have a distribution of Sn. And we're interested in what is this distribution. We have nothing about these xi's except the fact that they're independently distributed from some distribution with the same expected value and variance. Well, of course, there are, yeah, well, yes, but, all their moments would also be the same. And so we're interested, though, in what is the distribution of Sn bar, or Sn here. What is this distribution? And we claim is that as n goes to infinity, this will become a normal distribution. So we say, basically, that Sn, this is like usually the way we say it. This is going to be basically Sn minus the expected value of that will just be n mu over the square root of n sigma squared, right? Which will be Sn minus n mu over root n sigma. And we claim that this will converge in distribution to some normal 0, 1 as n goes to infinity. And we could also claim, again, we could think of xn bar. So let's think about xn bar here, which we'll define to be Sn over n. And what we're going to say is that basically xn bar minus the expectation of xn bar will be xn bar minus mu over, we know this is going to just be sigma squared over n. So we'll get sigma over root n. This also converges in distribution to normal 0, 1 as n goes to infinity. Right, and the reason this is true, I'll just do it. So this will be basically 1 over n times the variance of xi, so sigma squared over n, and then we take the square root, so we get some sigma over root n, okay? But the idea basically, here, I'm gonna erase this, is that we didn't say anything, so again, we need IID here, so these are drawn IID. And usually we say that this is less than infinity. But the idea is, more or less, is that we don't know anything about these xi's. We have no idea. These xi's could be drawn from some uniform, some normal, right? If it's normal, we know normal. We don't need n to go to infinity. But, these xi's could be from any distribution. From any underlying distribution. This is the key. Any. From any underlying distribution. That is the key. And this will also hold. So that's a central limit theorem 101. Yeah, I'm not going to prove it. I'm not going to prove it or anything, but yeah, that's the idea. yeah, so hopefully that was pretty useful.